Powering a spacecraft in the outer solar system is no easy feat. At Saturn's distance from the Sun, solar energy is too weak to be practical. That's why Cassini was equipped with something a bit more powerful and a lot more controversial: radioactive plutonium. Specifically, Cassini was powered by about 33 kilograms of plutonium-238, packed into radioisotope thermoelectric generators, or RTGs. These devices don't rely on combustion or fission like a nuclear reactor. Instead, they convert the heat released by radioactive decay directly into electricity. Even toward the end of its mission, Cassini's RTGs were still generating approximately 700 watts of power, enough to keep the spacecraft's systems running and its scientific instruments operational. The longevity of this power supply allowed Cassini to remain functional for over 20 years, including 13 years in Saturn's orbit. But carrying plutonium into space was not a decision made lightly. Had the launch gone wrong, or had Cassini re-entered Earth's atmosphere during its gravity assist without control, the consequences could have been dire. NASA ran worst-case scenario models and estimated that, if the plutonium dispersed globally, it might have caused around 5,000 cancer deaths, a projection based on long-term radiation exposure. That number was hypothetical and depended on a global dispersal that was highly unlikely. NASA concluded that the risk of such a disaster was about 1 in a million. And in the context of the potential scientific reward, the risk was deemed acceptable. Still, the public voiced concerns. Environmental advocacy groups challenged the launch and questioned the ethics of using radioactive materials in space exploration. NASA responded with transparency, detailing every safety measure and emphasizing that the plutonium was encased in protective layers designed to withstand high-velocity impacts and extreme heat. Fortunately, those safety precautions were never tested. Cassini launched flawlessly, soared past Venus and Earth, and began its journey towards Saturn, powered by a technology that had proven reliable on earlier missions like Voyager and Galileo. The RTGs weren't just powering basic systems. They supported a suite of advanced instruments, cameras, sensors, and communications. Every stunning image of Saturn's rings, every atmospheric analysis of Titan, every magnetic field reading, all of it was made possible by those glowing plutonium cores. In many ways, Cassini's power source was a symbol of the mission itself: daring, forward-thinking, and willing to push boundaries. And even at the end, the power was still flowing. Cassini didn't shut down because it ran out of energy. It ran out of fuel. Fuel, in this case, refers to the propellant used to adjust Cassini's position and orientation in space. Without it, the spacecraft couldn't change direction or stabilize itself to send data back to Earth. So, in 2017, when the last drops of propellant were nearly gone, NASA made a bold decision. Rather than let Cassini drift and potentially crash into one of Saturn's moons, especially those that might harbor life, the spacecraft would be sent into Saturn itself. This grand finale was both a dramatic end and a strategic one. It allowed Cassini to collect groundbreaking data as it plunged between Saturn and its rings, a region no spacecraft had entered before. These final orbits provided detailed information about the planet's atmosphere and gravity field, insights that would have been impossible to obtain otherwise. And so, the very source of Cassini's power, that little bit of plutonium, helped guide it from Earth, through space, into orbit, and finally, into the clouds of Saturn itself. In the next segment, we'll take a closer look at the instruments aboard Cassini, the high-tech tools that turned radioactive heat into revolutionary science. From infrared spectrometers to cosmic dust analyzers, we'll explore how Cassini became one of the most capable scientific machines ever launched. Stay curious and keep exploring with infinity beyond.